So this is statics and strengths of materials, Tuesday night, April 14th at 6 o'clock. And we are starting out with a little bit of review for the shear moment diagram for the deck 2x10 joists. And we had given the loading diagram. We went through the loading. It was 85 PLF. We had the span between the reactions, 13.83, a little bit of an overhang, a little over 2 feet, 2 foot, 2 inch overhang. And so we had room for area 1 calcs. And this goes right by the step-by-step procedure that we generated on PowerPoint. And this handout right here, okay? So just keep using that. We're going to go through a bunch of another problem after this one tonight. So the shear diagram always starts at 0, right? And it's, I don't know if you watched The Wizard of Oz last Friday night. I did. Follow the yellow brick road. And had nightmares because I always have nightmares about the Wicked Witch of the West. But that's another story. So this is the start of the yellow brick road. And the shear from there, remember JN always said to cover the beam. So the shear is going to go from 0 up to the first reaction, 573.3. Okay. And
Professor, I don't know if we're supposed to look at something, but all we see is your face.
Really?
Yes.
Well, thank you. Finally, somebody said something.
I'm looking at the homework.
Yeah, I can see your homework.
I'm able to see the homework.
Yep.
Well, whoever spoke up.
Swipe your screen to the left.
To my left. Oh, okay. I got it. Never mind. My bad. Sorry for interrupting.
No, that's okay. That's okay. We never had that problem in the pit. We could see each other's faces. Anyway, so again, you start at 0. The first load you see is a concentrated load. It's R1, the reaction, which is 573.3. So we go straight up to 573.3, and then every foot in a straight sloped line, that shear curve is going to drop how many pounds? 85 pounds every foot. So what we can say is that 573.3 minus, in parentheses, 13.83 times 85 for a total drop of 85 times 13.83, about 1176. From a positive of 573 gives you a shear value just before R2 of minus 602.3. Minus 602.3. And I'll go over another example. It's actually a fixed end reaction later tonight. We'll generate the reactions, we'll do the shear moment diagrams, and then a bending stress. So we're at negative 602.3, just to the left of R2. Well, at negative 602.3, you then have to add R2, which is 786.7. So adding 786.7 to a negative 602.3. No. Follow right up there, Yellow Brick Road, up to 184.5 pounds. These are all in pounds on the shear curve. Some of you are still not drawing in that x-axis, which is the 0 line of shear. Okay. At 185.4, we have one little section of the span to analyze. And so it's 184.5 minus 2.17 feet times 85 pounds for every foot. That gives me a finished shear at 0.1 pounds, which is a rounding off error. So that's why I put a line through there. And it's at 0 pounds. It's at 0 pounds. Okay. Does that make sense or not? Okay. So we cross the 0 line of shear. That's critical, especially in concrete beam construction because of the rebar orientation. So we have to find this run, this distance from the left end of the beam to where the shear crosses the 0 line. And that's that slope formula that I was telling you about. Some of you are struggling with that. So the run, which is that X, is equal to the drop. It's going to drop over that distance from 573.3 down to 0. So that is the drop divided by the slope. And that's 6.74. We could say that this distance, this distance from here to here is just 13.83 minus this. Or we could say it's, hey, I'm going to drop 602.3 from here to here at a slope of 85 pounds per foot. And that will also come out to 7.09. Okay. Excuse me. So you need that to calculate the areas. We're calculating the areas under the shear curve. Okay. Now, we have 3 areas. Area 1 is positive. Area 2 is negative. Area 3 is positive. Now, some of you took this distance, this 13.83, and just said that, hey, that's this is halfway, half of 13.83. It's close, but it's not exact. Okay, so you got to use that slope equation. Okay, the maximum shear is always the largest value at any point along the beam. Not between points, but at any point on the beam. So here, don't forget, at every concentrated and reaction load is a concentrated load, I have 2 values of shear, 0 and 573.3. I have 2 values of shear at this reaction. I got 184.5 and minus 602. That's actually the reaction value itself. And that is Vmax. We're going to need that for the next few calculations. Okay. So my maximum shear at any point, not between points, but at any point is right here. It's almost like the absolute value or the total range of shear values at any point. Area 1 is a triangle. Some of you forget the half. So that threw your numbers off. Okay. Whoops, should go to area 1, shouldn't I? So the area 1, that's 1/2 the shear times the distance. 573.3. That distance is 6.74 for a value of 1932.0 foot-pounds. Okay. Anybody in the waiting room, you see? 28, not bad. Am I going slow enough?
Yeah.
Everybody's asleep?
Yes.
There we go. So that's area 1. Area 2, it's negative. It's 1/2 minus 602.3 times that 7.9. That's negative 2135.2 foot-pounds. Area 3, it's positive. It's very small. 1/2 base times height, which is now 1/2 shear times distance. Foot-pounds. Positive 202.2. And this is where I got to be honest with you, I was disappointed if you didn't use my hints. And my hint was this actual drawing without these numbers. I showed you what the shear diagram was going to look like, and I showed you what the moment diagram was going to look like. And some of you are still fighting me. I take that very personal. Use the hints. That's how I passed my PE. Look for as many hints as I could. So the value of the moment curve at every significant point, well, at the beginning and the end, the moment is always 0. We'll show you an example later tonight where it's not 0. So right here is a significant point where it crosses the 0 curve. That's equal to area 1, which is 1932.0. Here's where you're struggling a little bit. This value is not the value of area 2. Okay. It is the value of whatever it was at this point, plus area 2, but area 2 is negative, or you can say it's just the value of area 1 plus area 2. In other words, the cumulative from the left side of the beam. But area 2 is a greater negative number than this is a positive number. So that's why it's got a little negative value right there. And it makes sense because the moment value at this point is the summation of all the areas. Area 1 plus area 2 plus area 3. If you take all of those areas, I came out with about a -3 foot-pounds. That's a rounding off error. Some of you came up to here, and then you came down to here, then here. Some of you were missing part of the moment curve. Try to find the pattern. That's the key. So again, 2 ways of describing it. This is area 1. This is area 1 plus area 2. This is, in other words, all the areas to the left on the shear curve. And this is the summation of all the areas to the left of this point. Or this value is whatever the moment is here plus that area 2. So look for that pattern. That's the key. Okay. Okay. Any questions on that? I'm just looking at my checklist.
How did you get the 184.5 for area 3?
How'd I get that value on the shear curve?
Yeah.
Are you with me right on this -602.3?
Yep.
Well, as JN said, you're basically covering, you're going from left to right, and just before that reaction, the value of the shear curve is -602.3. When you add the reaction, 786.7, 786.7 plus a -602.3 is 184.5.
Okay. Yep.
Now, what I want you to do, and again, especially if you're taking structural theory, literally go through those steps that I gave you. Right here. And that's telling you what you're doing. Like this one drops that 4,500 pounds. Right here, the shear goes up, whatever the value of R1 is. Here, the shear is going to go up positive because, again, I have the right end reaction. So you want to go through those checklists. I think, you know, if you follow those, like the first thing, draw light lines down. That's the first thing you always do. So think about that. Okay. Now what we're going to do is we're going to talk about the stress calcs. And this is what we talked about. You have this online, the shear and bending stress formulas. And what JN does is he gives you the step-by-step, how it's done. So you want to save this for structural theory, because Mr. H is going to go over this right off the bat. I think he got about a week and a half or 2 weeks of statics review, mainly units, and then he's right into beam analysis. So the first thing you do is you find the reactions. We did that. The second thing is you're going to construct shear and moment diagrams. We did that. We find the maximum value of shear, and we're going to get the maximum value of moment. And eventually we're going to convert that to inch pounds. And here's the formulas that we're going to deal with. So I think what we're going to do is we're going to call a homework assignment. We're going to call a home, and I'm going to do it right on the board. So all you got to do is copy it down. It's easy, 20 points, even for the folks who couldn't make this lecture, because I'll record this. Let me make sure I'm still recording this damn thing. Yep. Okay. So we're going to run the calcs, and that's where I'm going to use my, my camera. And these are the calcs. Now right here, this FV, which is 3V over 2A, the V is Vmax, and the A is the cross-sectional area. It's the cross-sectional area. This is for horizontal shear. It's for horizontal shear. V over A is for vertical shear. So we're gonna talk about horizontal shear. Okay. And then we're going to analyze it versus the allowable. We'll talk about that in a minute. So let's go to everybody on this page. And now what I'm going to do is I'm going to go to the camera.
What is this on Venko?
Oh, I got to hit the share. Okay. And you see the whiteboard if I get the hell out of the way. Everybody see that?
Yeah.
Okay. Whoops. Now what we're going to do is we're going to, this is the, let me see, this is the deck joist. And what was Vmax, folks? Bueller?
Vmax.
786.7. Hashtag. It's a 2x10. Which is 1.5. Is that 9 1/4 or 9 1/2? I can never remember.
I think it's 9 1/4.
Good. Okay. So the area, cross-sectional, is equal to 1.5 inches times 9.25 inches equals, go ahead and plug and chug that, 13.88 inches squared. Boy, that's coming out pretty damn good. I'm getting millions of hits on YouTube. This is great. That joke's still not working. Didn't work with a freshman either. Okay.
So that's the area of like the it's just the cross-sectional area.
Yep. So it's 1.5 inches, 9.25 inches. And that's the cross-sectional area. Right?
would that be in like the labs case, like the resisting area?
Yes. Yep. So the shear stress, little FV, is equal to 3/2 or 1.5 V max over area, cross-sectional area, XS. Okay? Well, we said that was 786.7 pounds divided by, whoops, we forgot the 3/2. 786.7 pounds divided by 13.88 inches squared. Little FV is equal to what? Go ahead and burp those numbers. So 1.5 times 786.7 divided by 13.88 equals 85 PSI. Pounds per square inch. We got somebody in the waiting room. Let's see the waiting room. Yep, I know that name. Oh shit, I missed it. Did I lose him? Mr. Dixon, are you in? Huh.
So for the lab that's due tomorrow, so we basically just gotta multiply by 3/2.
No. We're not on that yet.
Oh, all right.
Okay, this is totally different. I mean, it's similar, but this is the deck. This is the deck problem. This is a continuation of using the shear moment diagram that you generated yesterday. Now, what's big FV? And it dealt with the golden rule. What's the golden rule? I got to look at the weight.
Pressure actual is less than or equal to pressure allowable?
Allowance.
Allowable.
That's the allowable. That's the allowable shear stress based on the material. So let's go to page, what we're going to do is we're going to share a new share. We're going to do the desktop. And then we're going to go to page 278 of the book. Can you see the book?
Yeah.
Yes.
Yeah.
Okay. So we got some wood products and we're just going to make, let's see, hem fir, southern pine, we'll call it Doug fir, larch, north. I don't know my woods that well, but let's go to shear stress. Allowable shear stress is, and maybe we're using a joist, a number 2. So we're going to say Doug fir, larch. Okay. It's 95 PSI, page 278. And I'm going to show the screen here in a minute. Now, we're going to talk about bending stress here in a minute. So while I'm on the book, up to the side, I'm going to write bending stress. And that's big FB. And what's my allowable bending stress? What's the number?
We're using number 2, you said, right?
Yep.
So that's 95 PSI.
No, that was shear. What's my bending stress?
Oh,
14,
1,450.
1450.
1450.
Okay. So let's go back to the shared screen. Let's go back to the camera. Okay. So right here is my bending stress that I'm going to use for my next round of calculations. Okay. Here's my allowable shear stress that we talked about, 95 PSI. We got that on page 278 of the textbook. So these calcs are what you're going to submit for homework, exactly the way I'm doing them. Okay? And that was right here is Doug for Larch. So are we safe in shear? Our actual shear, ACT, this is a V. Our actual shear is 85 PSI based on the maximum shear and the cross-sectional area. Okay, our actual shear is 85. We're allowed 95. We're safe in shear. That's slicing load. You okay with that?
Yes.
That's the golden rule. Isn't that amazing? Okay. I wish I had Dan Aykroyd's voice. So let's erase. I'm going to erase this. You okay with that?
Yeah.
Was that a yes or a?
Yes.
Yes.
Yep.
Yes, sir.
A? Now we're going to go into the bending stress formula. And let's go to share screen, new share, desktop, share. I gotta check this out. And the bending stress was MC over I. Okay. M is what? Maximum moment. C is the distance from the center of the beam to the extreme fiber, and I is the moment of inertia. But we're going to cheat a little bit, and we're going to call it M over S. And M over S is called a section modulus. A section modulus. And the buzzword for that is depth. The deeper the beam, the more load the beam can handle. In other words, if you made your deck joists out of 2x4s, the depth of that 2x4 is 3.5 inches. The depth of the 2x10 is 9.25. So of course, the deeper beam is the 2x10. You're going to see this on the units quiz this week. We're going to launch that probably tomorrow. Okay. So we're going to use this M over S. It's just easier. Very basic section modulus, very basic formula. So let's start doing that. And yeah, here it is over here. Okay. So this is S, big S is section modulus. Buzzword is depth. So we're going to share the screen with the camera, share it. We're going to go back to our calcs. Our area, actually we don't need the area because it's M over S. So the bending stress, little FB, is M max over big S, which is the section modulus. Section modulus. What was the maximum moment, folks, from the homework that you did that was due last night?
Maximum modulus?
1,932
And what are the units?
foot-pounds.
Foot-pounds. And we have to divide that by S. Now S, over here, S, for a rectangular cross-section, BH squared over 6. I hope. I gotta look it up. Yep. BH squared over 6. Okay. Now the base is 1.5. The height is 9.25 inches square divided by 6. So the section modulus is 1.5 times 9.25 squared divided by 6 equals 21.39. What are the units?
Inches squared.
Oh, that'd be a good units quiz question.
Isn't it inch?
Nope.
Inches cubed.
Thank you. Inches times inches squared is inches cubed. So I put that over here. But there's a problem there. Whoops. There's a problem there. This is in foot-pounds. This is in inches cubed. What do I have to do?
Convert it.
Convert it. I'm going to take this out so I got some room. And here's my good old dimensional analysis. If I want to get rid of feet, I put feet on the bottom. The voodoo that we do, 1 foot is 12 inches. It's not squared, so I leave it alone. Feet cancel. So now it's 1932, right? Times pounds in inches, times 12, divided by 21.39. Times 1932 times 12. Little FB is equal to
How did we end up?
1,084 pounds per square inch. That's the bending stress, the bending pressure based on the NMAX of 1932 pounds. 1932 foot-pounds. Okay. What am I going to compare that to?
The allowable.
And the allowable, big FV, big FB was 1450 based on the type of wood, the species of wood, which was pounds per square inch. Is it safe in bending?
Yes.
Isn't that amazing? So it's safe in bending. Okay. And that is the analysis of the deck joist. Okay. So if I'd have had maybe, let's just say, just for the heck of it, what if I had a 2x4? So that would have been 1.5, so that would be 3.5 squared. I'm not even going to write it down. Times 1.5 divided by 6. That's only got a section modulus of 3 times 1932 times 12. It would have had a bending stress of over 7,500 psi. But it's only allowed 1450. And before it failed, it would have had one hell of a deflection, which is the next thing we're going to check probably next week. We're going to go actual deflection formulas, and we're going to calculate, we're going to compare that to allowable deflection. And I got some great photos of an old pavilion before they tore it down in Delhi. You would not believe the deflection. I couldn't believe the thing didn't fall down. Okay. So those are the calcs. You've got to submit those for a grade exactly the way I just wrote them. And what's a good time to submit those? I mean, for you folks, hell, you could submit them tonight. But for the people that are not here, let's see, we said tomorrow night for the lab calcs. How about Thursday night?
Sounds good.
I mean, we're literally just submitting what we just did.
Just what you did.
It doesn't matter if we submit it early, right?
Correct. I just tonight I'll set up the Dropbox. So I'm going to note this is 4/16 at 11:59 p.m. And again, we're recording this, so I'm going to post this to YouTube. So the rest of the folks, can look through it.
Sounds good.
So I'm just going through my checklist. The shear lab data. So let's go with sharing the screen. A new share right to here. And we have the lab. Here's the new one that I posted, because one of you was nice enough to tell me that I screwed up and did not give you the, I don't know why I keep losing the photon torpedo there. I didn't put the load. So what I did there is I added a new column to the wood and asking, is that in single or double shear? So this picture of the wood, is that in single or double shear? So what is it, single or double?
Isn't it a double?
It's double because you have two glued surfaces. So that's like with the dowels, you have two sections of the dowel, if you will, that is resisting the load. So they're both in double shear. So you got to take their area, right? Whatever their area is of one glued surface or one dowel cross section, and double it. And so that's your load divided by your resisting area. Don't worry about the failure type. We talked about that. I'm not going to, we'll discuss that next week sometime. I'm just looking for these calcs. So you have to fill in all of the chart, and you only have to show me two calcs, the Gorilla Glue calcs and the steel dowel calcs. And this is all due, these calcs are due tomorrow night, Wednesday.
What calcs are we doing?
What's
So is
that?
it similar to what we just did?
For calcs we're showing?
I didn't hear the question.
Is it similar to what we just did?
No.
There's two different things.
I mean, it's still dealing with shear, but this is a lab experiment. So what is your glued surface here, right? The width is the width of a 2x4, and the height, this 4 inches, is right here. This is 4 inches. So I have 3.5 inches by 4. That's a little over 12
That's 14.
inches, but you got to multiply that by 2, and that's your area. So that's just straight. This is vertical shear. Okay. This is vertical shear that we're dealing with here.
But when you get that area, do you just divide that 9,000 by that area, or do you have to do
Yes.
3/2 with it?
Nope. Oh, good question. This is,
You're the famous Angelina.
let's see, can I do that? This is equal,
You did the same thing you did to her here earlier.
oh, this is a PDF.
Same thing to Melissa. here.
Mic off.
Yeah.
Hey, guys, little quiet there, please. So this, do not use,
Oh, first of all, look at this.
Let me look at Jason right there.
Rashid, this is me though.
Mm-hmm.
Turn your mic off.
I've seen most of your young.
so for this shear, this is vertical shear. This is critical. And the formula for vertical shear is just load over area, load over cross-sectional area.
All right.
Horizontal shear is that 3/2 times shear divided by area. Good question. Good
And
question.
also for the dowel, you don't have to times the area by 2, right? Or do you?
Yeah. Let me just write, so this is P over A. I'll update that again. Yes, because the dowels are in double shear.
All right.
There's a dowel right here, there's a shear plane right here, and there's a shear plane right here. So
Gotcha.
they're both in double shear. They're both in double shear.
So
That's a good question. I appreciate that. Plus, that puts me in a good mood.
the dowel data type, when it's asking for single and double, you just want us to write double for the steel dowel?
Yeah, you'll write a 2 because that'll remind you to multiply the area times 2.
Can I explain to you what I did to get my, because I tried it, I don't know if it's correct now.
Yeah.
I did the 3.5 times 4, which equals to 14 times 2, and then I divide that by the 9,000. Is that correct?
Oh, it's 9,000 divided by combined 3.5 times 4 times 2.
Yeah.
Shear. The way you worked it, you said that it was area divided by load. It's load divided by area.
So it's
Okay.
9,000 divided by 28 would be your answer.
Yeah, that makes sense.
Yep. So I'll update that little handout. This is due tomorrow night. Calc's right here, Gorilla Glue steel. And so because if we don't do a Saturday Zoom, let me do a little bit extra, an additional problem. And so what we're going to do is go to page 379, which was chapter 8. And we're doing problem 8.1. We're doing problem 8.1. Okay.
And we're doing that on Saturday?
Now I'm going to do that right now.
Okay.
And that'll be a problem if enough people want to watch a Zoom on Saturday, I will. So we're going to do 8.1. So draw yourself a little sketch right here. Draw a neat sketch. This is a cantilever or a fixed end reaction. So if you look at this, this is a fixed end reaction. It's really what my balcony. Right? So I'm right at that window. So this is a fixed end reaction, and it's very similar to that.
And when will this be due?
I haven't decided yet.
Okay.
So we're just going to start that because you're going to see this in structural theory a lot next semester. Okay. So start sketching as I erase, and then I'll start we'll start running the calcs there. And we're going to go through just about all the calcs on this because we have not talked about this type of beam much at all. Okay. So that's what you got right there. We're going to do a new share. And we're going to go with the camera. And we're going back to the new whiteboard. Okay, so I'm going to draw this. I'm not going to draw it that well. I'll try to draw it neat. Where the hell is that book? There. Okay, so that's going to be what they call a fixed end reaction. This is a free body diagram. And it's got what's the load at the end?
2,000.
2,000 pounds. And what is the size of the beam? Can you see that? 2,000 pounds. What is the size of the beam?
W8 times 18.
Right. So it's a W8 by 18. And the W is a wide flange. So it's going to look like this. The 8 is the nominal. That's the nominal depth. It's not 8, it's close. It's like a 2x4 is not a 2x4. And what does 18 stand for?
Isn't that the
That's the linear load. Okay, 18 PLF. Okay. And do they give it a, they don't. So we're going to say this is R1. And there's only one reaction, but there is a built-in moment carrying capability. It has a built-in moment. This is the moment at R1. In other words, that, like my balcony, this thing is socketed into the wall, right? It's like a power pole. Only now, instead of socketed into the ground vertically, it's horizontal, if you will. Okay? So, let's see if this will fit on here. Yes, it is. So we're going to do the sum of the moments. Actually, no. To get R1, this is called a fixed end reaction. A fixed end reaction, that's ancient Babylonian Sanskrit for an N. And so we're just going to say the sum of the forces up equals sum of the forces down. These are easy to do for the reaction. What forces are acting up? What vertical forces? Oh, some of the forces in the Y direction. So what forces are acting up vertically?
Reaction 1.
Reaction 1. What are the forces acting down?
2,000 pounds and the 18.
Yeah, but it's 18 pounds per foot. Let's say that this is 10 feet. Makes it easier. I like easy math, okay? So it's a 10-foot long beam. So it's 18 pounds per foot time, and what do I have to multiply that by? 10 feet, because that's the span of the W8 by 18. So R1 is equal to 2180, right? So R1 is equal to 2180. Hashtag. Again, there is not a second reaction, but it does have that built-in moment carrying capability. Now we're going to take the sum of the moments about R1. Positive is clockwise. Positive is clockwise. So it's equal to, sum of the moments equal to 0. The moment at R1, is that going about this point clockwise or counterclockwise? Is this moment going clockwise, which means it's positive? The moment at R1, it is a moment, so it's not forced. It doesn't need a force times a distance. It is a built-in moment. That's the type of reaction that we're dealing with. Okay. What do we have to do here? How about the 2,000-pound load? Is that going clockwise or counterclockwise about this point right here? It's going counterclockwise times what?
10 feet?
10 feet.
Right, 10 feet. Okay. Now I don't have enough room to go this way because I'm going to take this off up here on the diagram. So right below here, it's as if this equation is just continuing underneath. But I got this linear load. Bless you. So what do I got to do with that? So I got to say minus 18 pounds per foot. It acts over 10 feet. So right there, that right there is what? That's the ECL. But I'm not showing the ECL because then you get confused and you start to put the ECL, the equivalent concentrated load, in your shear moment diagram, and that's not a good thing. So that's the ECL, which is really right here, acts through the center of the beam. So what is its moment arm? Your load, its equivalent concentrated load is how far from here?
5 feet.
5 feet.
Yeah.
So that's linear load times the distance that the linear load acts upon is a load. Linear load times distance equals a load. Times the moment arm. Okay? Times the moment arm. And so using the voodoo that we do, we got all of this, stuff. It'll burp over to this side. And so MR1 the moment at R1, oops, can you see that? Maybe not.
No.
The moment at R1 that's 20,000. So that's 2,000. So you got to get good at the algebra. Times 10 plus 18 times 50. That's 20,900. 20,900 foot-pounds, which is this, which is minus 20,000, and this is 900. That's 20,900. It's all negative, and then you put it on the other side of the equal. And so it's a positive because it's going clockwise about R1. Okay. You won't see that. You won't see this on a test here this semester. You will see it in structural theory. So you'll have some examples to use, and that's why we wanted to go over some examples. Okay, so these are the, right? So there, that's how you do the reactions.
How did you get the 20,900 again?
Okay, you got to do the algebra. So it's 0 is equal to the moment.
Yeah.
And this 2,000 times 10 is 20,000, but it's negative. 18 times 10 times 5 is 900. That's negative. So that's added to the minus 20,000. That's minus 20,900. It's all negative. So you bring it over to the other side of the equals.
Oh, all right.
Okay. Cough drop here. Guess what we're going to do now? Shear moment diagram. So what do? You draw a light line straight down.
Shear moment diagram.
Do I draw a straight line down at the ECL? No.
So you got to yeah, let's dive in head first.
Okay. The shear always starts at 0. And what you're doing is you're following the loading diagram like you're following the yellow brick road. So it starts at 0, and what is it immediately going to do while at 0?
Go down 2,000.
Go down 2,000. Okay? And you really got to work on your labels, your values of the moment curve. So let's see. Let's see if you can, let's try this here. If I can stop shaking. Okay, I'm going to clear this. So I'm going to say 0 minus 2,000, okay, equals. So that's the value of the shear curve at this point. How much is it going to drop? For every foot, it's going to drop what?
18 feet.
18 pounds. So if you had something where the math wasn't that easy, you could say minus left parentheses 18 times 10 right parentheses, so that at the end of that 10-foot span, my shear is going to be minus 2180. Well, the math is easy. This is 180. It's going to go down negative, and it's going to go at a slope of 18 pounds per foot. Oop, that's supposed to be straight. Okay, so there's only one area, but then what does it do? It's got to go back up R1, but R1 is 2180. Isn't that amazing? Goes up to 0. And that's where you want to get into that pattern of doing your shear diagram. You're following the yellow brick road on loads. 0, dropping down 2,000. Every foot I go, I'm dropping 18 pounds. Over a total of 10 feet, I've dropped 180 from negative 2,000, so I'm negative 2180. Plus R1. So this right here is V max. Is V max. So, yeah, let's do the moment curve. So this is area 1. And what is that shape?
It's a trapezoid.
Trapezoid. Don't call it a triangle and a rectangle. It is, but make it easy on yourself. Okay? So area 1 is equal to, and it's negative, minus 2,000 pounds plus negative 2180 pounds divided by 2. Damn it, I ran out of room. Times 10 feet. It's force times distance. It's the average of the two shears times 10. So that's 4180 divided by 2 is 2090? No.
Yeah.
Oh, 20,000, 20,900. I forgot to multiply it. So it's 4180. This is 4180, it's negative, times, or 4180 divided by 2 times 10, 20,900. Foot pounds.
Which equals MR1.
Exactly. Isn't that amazing? So the moment curve over here, it starts at 0, but it doesn't end it. Eventually it ends at 0, but it doesn't end at 0 right away. This is going to be a curve. Did you hear that? It's keeping you awake. God, I miss you people. Jeez. So, and that was a negative area. There's nobody to get cranky at. So that's negative 20,900. And then that goes back to 0 because that's MR1. And so that's going to be N max, right? So what I think we'll do for homework for this is we will have you analyze shear and bending stresses. Okay? Shear and bending stresses. So, does anybody need these calcs for the reactions? You got them all? Okay, I'll take that as a yes. Plus, it's on recording. Okay. So now we're going to use shear, and it's going to be V max is equal to what? Minus 2180. Little shear, and this is V is shear. Now it's just going to be load over area. That other one for horizontal shear was just wood. So we're just going to go load over area. Okay.
What are these calcs for?
These are the stress calcs. It's exactly what we did for the beam deck joists. We got the reactions. We got the shear moment diagram. We got Vmax, we got Mmax, and now we got to see if it's safe in shear and bending. Okay? So from page 278, okay, big FV is equal to, page 278, we're going to say that it is A36 steel, is 14.5 KSI. What's KSI?
Kips per square inch.
Kips per square inch.
Yes, sir.
Now, let's give you the bending stress formula. What was that? That was Mmax divided by S. And big FB is 22 KSI. Now this is going to be your easy homework. In other words, you're going to copy everything that I've done, right? The only calculations you got to do are these two and tell me whether they're safe in shear and safe in bending. And then this won't be due, say, probably Sunday or Monday night, and then I'll probably do a Zoom on, Saturday, and then record it if anybody has any questions. If you don't, you don't.
What's the difference between the little FB and the big FB? I guess I kind of missed that.
Okay, the little f is always the actual.
Oh, okay.
The big F is what you're allowed based on the material. Well, this is A36 steel. Okay, but where do I find A and S? Well, I'm glad you asked. I'm glad you asked. This and this on page 572 of the text. Okay, and then what I'm going to do is I'm going to switch screens, a new share. I'm going to do desktop. I'm going to share it here. I'm going back to the book, and I think I said page 572. So, can you see the book?
Yep.
I got to go back with a photon torpedo here. Here we go. So there, where's my, I got a W8. How would I get this little bugger out of there? Oh, that's how you do it. Isn't that amazing? So, a W8 by 18. There it is. Okay. Now, where the hell is area here? Area of section. And it's S, it's the higher, see SX and SY. It depends on how you orient it. In other words, is it a 2x4 or a 4x2? Okay. You take the bigger of the two. So which one was that? That was right here. So there's, you got 15.2, which is your section modulus. 5.26 is your cross-sectional area. And then you can run the actual shear stress and the actual shear, sorry, oh, watch my language. I shouldn't have said that. The actual bending stress. Damn it, I forgot to get Haggard on YouTube now that I'm doing some screen work. Okay, so we'll get that on for Saturday. I'll start, I gotta write Haggard down. Haggard. That way I can't get in too much trouble. I'll have to watch my language. Okay, so if we go back to the shared screen, and we go back to the camera. Got to hit that button there, Stephen. So I just showed you that this was the area. So that's the Vmax from the shear diagram. And the area I just showed you from page 572. And then the Nmax, and I showed you the section modulus. But Nmax has to be converted to inch pounds from foot pounds. And that tests the golden rule. Are your actual stresses less than what's allowed based on the type of material that you're using? And we're really starting to close the loop. That's everybody's favorite phrase now, closing the loop with statics and strengths of materials. You know, everybody loves that phrase, closing the loop with learning objectives. Okay, well, we went about an extra half hour. I do appreciate your patience. This will probably be due Sunday or Monday, and it's basically going to be everything that you see. You can rewind it, because I'm going to put it to a YouTube, and you're going to walk yourself down the yellow brick road based on JN's notes of finding reactions, finding shear moment diagrams, finding actual stresses, comparing them to allowable stresses. Okay? Any questions?
For the FV is equal to the Vmax over A, do we have to use the 3/2? Or that's
No, you're just going to use this.
Okay, all right.
Yep. For the other one you did, but not for this one.
Okay.
Okay. So I think that's about it. Thank you. God, I don't like looking at the camera. But let's do a share to the desktop. And good. I feel more comfortable looking at that damn thing. Although maybe Hollywood will call and they need a common person in a movie. Who knows? If you can get into this pattern, especially for you folks who are you're taking structural theory, and you get comfortable with knowing these patterns, you're going to be in good shape. So really what we're doing is we're following this for stresses, and then we're actually following this for shear moment diagrams, and then you've got another one on reactions, okay? So I'm going to, what am I going to do? I'm going to stop